Previous videos in the playlist looked at this particular diagram here, which showed all of the 4 essential managers you expect to find in an operating system and how they cooperate with one another to perform the functions of a typical operating system. In this particular video, I wish to concentrate on the memory manager. What we need to do is to consider the main tasks of the memory manager. Now, the first thing to say is when we're talking about the memory manager, we have to realize that it is in charge of the main memory. And by this, we mean the random access memory, the silicon memory, not the disk system. That's something different. We're talking about where we store the programs that have their machine code fetched, decoded, and executed. A memory manager allocates space to programs within the random access memory, and these programs, when they run, we know become processes. So we can say that the main purpose of a memory manager is checks the validity of each request for memory space. If it is a legal request, it allocates a portion of memory that isn't already in use. In other words, the memory manager has to keep track of what's in its memory and where in the memory it has free space to allow the entry of other programs that may become processes at a future point in time. Of course, we could have a computer system that allows more than one person to actually run their processes from a particular computer. So you might have a computer that has connected to it 5 dumb terminals, and you currently have 5 people logged onto that computer. Now, in those circumstances, each individual would have to be given their own area of the computer's memory. So a task of the memory manager in a multi-user environment, the memory manager sets up a table to keep track of who is using which section of a computer's memory. So in a sense, you actually say, well, person A is going to have this chunk of the memory, person B is going to have this chunk for whatever they're doing with their particular logon session. Of course, the memory manager keeps a check on where in RAM there are programs loaded and data loaded. It also keeps a check at the spaces in memory that are not currently being used. Now, when a process ends, it may be the case that we can free up the space that was taken in the random access memory. So when the time comes to reclaim the memory manager deallocates the memory. And we'll have a look at what this means with an animation in a moment. Right, let's consider this simplified view of a computer's memory. Here you can see I've got a memory location. Here's another memory location, here's another, and you can see they follow on. These squiggles here, well, they mean that there's lots of memory locations between this location and this one. Here we can see we've got the squiggles implying there's lots of locations here, and those squiggles are there simply because we cannot really draw every memory location on a simple slide like this, because memories inside computers are millions and millions and millions of individual memory locations. So down here you can see I've put a couple of squiggles which indicate that the memory goes on for a lot further. Here you can see I've labeled this as address 0. This one here is address 800 and this one is address 801. Now, I don't want you to get too hung up on these addresses. I am not saying these are the actual physical addresses you will get when you build your computer system. For example, here this is 800, and in memory systems the next location most probably would be not 801, it would be an address that was 804, because the individual address locations might take up 4 bytes, for example. So these are not a true reflection of the actual hardware that we see, but they're just an approximation to allow us to look at how a memory manager actually works. So these addresses here are simply to tell us, well, look, if this is address 800, this is the following address 801. And down here you can see I've got address n, where n represents a number, and of course this is n minus 1 because it will be one number less than address n. So if address n, for example, was 1000, then n minus 1 is obviously 999. So I've just simply here got a simplified memory in terms of the way in which I'm writing down the addresses. As you look at the video, you can see there is a red dotted line, and as you're looking at it, to the right of the line you can see we've drawn the memory, and to the left of this line you can see that it says Central Processing Unit. Now there's obviously a bus system between them, but I'm simplifying things here. So what we're now going to say is, how do we load the memory, the random access memory, with a program? Let's say the user's clicked on something, which means they want to run a program. The program is not in random access memory, so we have to go and get it off disk and so on. I'm not not going to be showing that here, but we need to know where in the computer's memory it's going to go. So the program comes in, and what we do, we have registers, and here you can see I've got a register with 900 in and a register with n-1 in. And what this will do, it'll point to address 900, and this one will point to address n-1. Now these are called boundary registers. And what they do, they point to the first and the last location of a program that we're going to load into the computer's memory. Now I can show that program with this yellow shading here. And what we need to be clear about is here I have actually shaded their background in yellow, and that's a pair of registers which will point to where in the computer's memory we have just loaded up a particular program. Of course, it's more than likely at any instance in time the computer's random access memory will be storing more than one program, and we have to monitor where all of the programs are. So in fact, this can be achieved by using another register pair, as I've shown here with the green background, where the first one is the first address of another and this one is the last address of another program that's actually loaded into the computer's memory. And of course they will point as appropriate. And I could have drawn the slide and shown the green shaded area, but I think it's pretty obvious is what this actually means. Now of course all of these registers here that are doing the pointing form what's called a table, and there will be lots of these registers pairs here. Now I'd like to emphasize that I'm simplifying things a little bit here, but this is the underlying principle of how we point to the areas of memory that are going to be used at any particular point in time. So the yellow shaded registers and the green shaded registers are actually pointing to programs that are currently in the computer's memory, and we are not allowed to use those areas for anything else. So for example, if a program came along and tried to write to these areas, the memory manager mustn't allow that to happen, because that is the machine code for a particular program that will become a process. So the memory manager has a responsibility to make sure that the request for a particular memory location is legal. If it's not legal, it wouldn't allow that to happen, and it'll do things called preempting, which we can talk about at some later date. But this general structure here of having things pointing to where in the memory we have the programs is fundamental to how memory managers actually work. Of course, there'll come a point in time when the program that's loaded into this particular area of the computer's random access memory is no longer needed. The user may have shut it down, for example. So we need to deallocate this area. We need to free it up. Now the process for doing that is pretty straightforward, and what it will involve is looking at these registers here and actually removing the addresses from them. And of course, when those addresses are removed, they no longer point to the region of the memory where the process used to be stored. Consequently, we free those registers up and we free this area of memory. Now what I'd like to emphasize here is in this region was all of the machine code instructions and all of the data that that particular process needed when it was running. That particular program was loaded here with all of its machine code and all of its data, assuming it fit. Where is it? Well, it's still there. It's not got rid of. We don't simply go and say, well, we'll get rid of it by setting all of these addresses to 0. That would just simply be too time consuming. What we do, we simply remove the register addresses from these register pairs, and now these register pairs are free to point to another program in the computer's memory, and we can see now that there's nothing to stop us writing to any of these locations, because the memory manager doesn't have that region pointed to as being something that currently has a program loaded into it. Now it's worth emphasizing that a primary responsibility of the memory manager is to protect the space in main memory occupied by the operating system itself. It can't allow any part of it to be accidentally or intentionally altered. Now there is a number of protections in place in terms of what the hardware can supply to stop this happening, and we'll be discussing that at some later date. But essentially what we have got here, when a computer boots up, the operating system is loaded into the random access memory, and it's loaded into a particular region of that memory, and it has to be protected. If it's not protected, obviously the corruption of the area of memory containing the operating system corrupts the operating system, and that's when we run into quite serious problems with our computers. They crash. let's talk about the relationship between the memory manager and the operating system. And of course, the memory manager is part of the operating system. But here you can see I've drawn a schematic diagram of the computer's memory, similar to one we've looked at earlier in this particular video. And you can see I've shaded the area in this rather unpleasant color of orange. Now that shaded area represents the operating system that was loaded into RAM when the computer was actually booted up. Now what we have within inside the computer are registers that are responsible for pointing to the first location and the last location of the operating system. Now I'm making some assumptions here. I'm making the assumption that the operating system takes up this space all the time. A lot of modern operating systems are object orientated, and the size of the operating system can alter as new objects are brought in to service particular tasks. But essentially we can say that operating systems are loaded into the RAM, and this is what we've got here. And we can see we have register pairs pointing to the first and last location of that operating system. Now these register pairs are specialized in the sense that when you write an application as a computer programmer, you don't have access to these registers, so you cannot alter them in any way. And there's something referred to as supervisor and user states of a central processing unit, which is something we can talk about again. But essentially any attempt to write into this space will cause an exception. So any attempt to actually alter what's between this address here and this address, in other words anywhere in this space, is captured. A trap is set. Now a trap, an exception and interrupts are all the hardware mechanisms that work together with the software. The software has this extra support from the hardware. But it's key to realize that we cannot actually corrupt the operating system. We must make sure that is not allowed to happen. Check out the supporting website for these videos and consider subscribing to the YouTube channel, and you'll get an automatic update every time I upload a new video.